Welcome to Talk Universe. I'm your host, Sir Charles Schultz, and Eliza.
What do you need?
Would you like to introduce the show, please?
Hello and welcome to Talk Universe. I'm Eliza and this is our show for Wednesday, February 22nd, 2017.
And what's the show's topic?
Tonight's topic is superconductors.
Fantastic. That sounds very interesting. There are a lot of things to know about superconductors. And Eliza, what is a superconductor?
What is a superconductor? It is a material that exhibits no resistance to the flow of electrical current.
Great. So what makes superconductors so important? Well, as it turns out, every material that we use to conduct electricity has a resistance to the flow. It fights back a little. In our world, there basically are only a small number of different types of compounds. There are insulators, which are materials that don't allow electricity to flow through them. There are conductors, such as metals, which allow current to flow, but generally have resistance, and some of them are pretty poor. Certain elements, for instance, lead, are poor conductors of electricity, whereas other elements, such as silver and gold and copper, are very good conductors of electricity and have low resistance. Then we have materials that are somewhere in the middle, that are resistors. Carbon and other materials mixed with carbon make pretty good resistors. We also have a specialty type of material, semiconductors. Now, semiconductors are special because their properties do not remain the same. Usually they're made of a synthetic crystal that's been doped with other elements to change the properties of the crystal. Germanium and silicon are the two most common types of semiconductors in times past. Today we use something called gallium arsenide. But by mixing other elements in it, we change the properties of the crystal so we can switch it on or off or somewhere in between. So a semiconductor is capable of being turned into a conductor or an insulator or a resistor, and it can do so dynamically. This is what makes microchips work. Semiconductors allow us to control the properties of the crystal in such a way that we can switch it on and off, control how it amplifies or conducts, or even if it emits light or detects light or does other things as well. But those materials are very specialized. When we get down to the task of conducting electrical power or making big magnets or motors, the resistance in the wiring turns out to be a real problem. Now, in some cases, we actually make wire that has high resistance intentionally. And one case is a mixture of chromium and nickel called nichrome. This is a high resistance wire that turns a lot of the electricity that passes through it into heat. If you've ever looked inside the toaster, that orange glowing curly thing inside there has caught your eye. You're looking at nichrome. In the heating element of your oven, there's a larger piece of nichrome, and it's wrapped in an insulator and a metal tube. And that metal tube keeps it from being charged with high voltage and killing you if you touch it, which would be rather inconvenient when you're cooking a roast or making some toast. So heating elements are made that intentionally have high resistance. But in the pursuit of making better motors, smaller machines, and more powerful magnets, and reducing the loss in electrical transmission, we've been looking for materials that have no resistance to the flow of electricity. Now, many people have wondered about that in times past. They noticed that as you heat a conductor, the resistance goes up, and the filament of a light bulb is an excellent example of that. The hotter the filament is, the more resistance it has to the flow of electricity. Some people have actually put this to use, and Hewlett-Packard, the company, was founded on this effect when they built an oscillator that used the filament of a light bulb as a varying resistance based on how much current was passing through it. But in the real world, we want the lowest possible resistance to get rid of the losses and to allow us to make magnets smaller and more powerful, for instance. Well, it was noticed that as you heated material, of course, the resistance went up, and the obverse was also true. When you cool materials, their resistance goes down. Now, there was a German physicist by the name of Kamerlingh Onnes, and in 1911 he succeeded in chilling a metal to the point where it actually lost all its resistance. He watched as its resistance began to slowly lower as he dropped the temperature, and using liquid helium, in 1911, he was able to take mercury, freeze it, and measure its resistance as it was cooling. And a very funny thing happened around 2 degrees Kelvin. And it's this. The resistance of the material suddenly dropped, clicked off like a switch, and it became a superconductor. Now, it's interesting. Many people wonder, why is there a certain lowest possible temperature? and superconduction happens near the lowest possible temperature. So why isn't? Couldn't you just keep making things colder and colder? The answer is no, and the reason's simple. Temperature is based on the molecular or atomic activity, vibration, or movement inside a substance. Everything is made of atoms, and those atoms vibrate and move around. And the hotter the substance is, the more vibration and movement those atoms have. Conversely, if you cool a material, it becomes less and less energetic, and the vibration, the movement of its constituent particles or atoms, becomes very, very small. Obviously, if they were standing still, those atoms would have no vibration whatsoever, and at that point the temperature would be absolute zero. You couldn't get any colder because there's no such thing as negative movement or anti-movement. Once the atoms are absolutely stationary, there is no thermal energy in them. Now, this is an important thing to understand. When we look at the thermometer, and most people in the US use the Fahrenheit scale, we notice that temperatures can be negative. Well, this is because mercury or alcohol solutions that were used to make thermometers in that day had a lowest possible temperature. They would freeze and you couldn't measure below those temperatures. The negative scale on the Fahrenheit scale was meant to be around the freezing point of a specific material, and everything below that temperature was negative. On the centigrade scale, a similar thing holds sway. Everything on the centigrade scale is based on the properties of water. 0 centigrade is the freezing point of water, and 100 centigrade is the boiling point of water. And it seemed like a very logical system. In fact, the centigrade, meaning having 100 graduations, the centigrade scale became very common in other countries and definitely in scientific work. When people tried experimenting with gases and measuring just how cold they could get, they discovered that there was a lowest possible temperature. And if you used the centigrade scale, it turned out to be minus 273.16. This is absolute zero. So the centigrade scale is used as the size of the degree, and the Kelvin scale was born. So the Kelvin scale has its zero at 0, absolute zero. Now, room temperature on the Kelvin scale would be about 300 degrees, and the freezing point of water would be 273 degrees Kelvin. Superconductivity always happened in the past at temperatures of 2 to 4 degrees Kelvin, very, very cold. And nothing would ever superconduct at a higher temperature. But in 1987, a researcher by the name of Paul Chu was able to find a mixture of materials, a type of ceramic, that actually had a transition temperature or a superconducting temperature around 89 degrees Kelvin. Now, what's significant about this is this. Practical effects are hard to bring into the real world sometimes. When we look at superconduction, we know that it would be something we would want to have for industrial machinery. But if it only happens at temperatures of liquid helium, it's too hard to maintain and it's too expensive because helium is not cheap. When you get to the range where liquid nitrogen can do the cooling, suddenly you've opened up a whole different world. Liquid nitrogen can boil at about 77 degrees Kelvin. The new superconductors discovered in 1987 can work at 89 degrees Kelvin. Cooling them with liquid nitrogen is economically very feasible, and suddenly superconduction became something that could be used to make powerful magnets, for example. So Paul Chu's work opened up a means of creating a class of ceramic superconductors that actually had very high transition temperatures. Eliza, what is transition temperature?
In superconductors, transition temperature is the temperature at which they lose all electrical resistance.
Thank you. Eliza, do we have any questions in our queue?
5 entries are still remaining, Charles.
That sounds great. Well, we're going to take a couple of those questions real fast. And we're also going to get into the reasons why superconductors are so important very shortly here. So now we have a basic understanding about lowest possible temperatures, and we also have an understanding that different materials in nature are pretty good superconductors, but ceramics turn out to be much better superconductors, and recently we've had much higher temperatures achieved with other materials. Practical magnets are now being made, and motors and other things as well, using superconducting ceramic materials. There's a very interesting story about how they get a ceramic to be a wire. So what would superconductors really mean to our world? Well, first of all, a lot of power is lost in transmission lines. Some people estimate 15%, and that's a pretty good number. It can be much higher during inclement weather such as rain or snow because of arcing. If we had superconducting power transmission lines, a lot of that power that's lost in transmission would be recovered or saved, and some cities are already doing that. How about magnets for linear accelerators or fusion research or even just everyday motors? Superconducting windings for motors would make motors much smaller, consume less power, and generate less heat. So they would mean immense savings in materials to make the motors and in the power wasted in the motor and better efficiency converting the incoming electricity into useful controlled movement. Superconductors would make a lot of big differences in our world. They're used in MRI machines, they're used in a lot of other applications around us all the time. And we're not even aware that liquid nitrogen-cooled superconductors are in a lot of the devices we use. If we could have room temperature superconductors, we could eliminate all the cooling, and it would make the transmission of power safer and more efficient, the construction of motors smaller, lighter, and more efficient, and the construction of desktop-sized scanning machines, things that would fit in a suitcase or even in the palm of your hand, quite possible. We're also looking at the construction of frictionless floating magnetic bearings and levitating trains that travel at high speed without contacting a rail or the ground at all. So a lot of things would change with room temperature superconductors. So, Eliza, are you ready to read a question or two?
Okay, Charles.
So read the first question, please.
Robert from Jacksonville asks about nuclear power plants. What do we do with nuclear power plants once they become obsolete?
That's a great question, Robert, and basically, right now, we don't have an easy method of disposing of old nuclear plants. In the future, we'll have to have better methods of going in and removing the radioactive materials that are left over. And there's a lot of nuclear waste stored in power plants right now, so that's a real issue. We do know how to handle it, but legally, it's not allowed in a lot of cases. We do have the means of recycling nuclear waste. So the big thing here is, once the things are shut down, we have to get a law in place that allows us to recycle the waste. And then we have to find ways of disposing of the old reactors properly. Cutting them up and hiding them in concrete isn't a good solution. We'll have to find a better way of doing that. Eliza, read the next question, please.
Dan from Jonesboro asks how soon before 3D printed body parts and tissue will become commonplace?
In some countries, it already is fairly common. They've been printing windpipes and simple things like that, and some are working on bladders and other functional organs as well, and that's been going on for over a decade. There are a lot of restrictions in the U.S. that don't allow it here, or only under very, very tight conditions. There seems to be a lot of objection by many in the medical community to using this technology for some reason. And that's something we've got to get around, because there are a lot of people, millions of people, who could use this technology right now. So in many cases, it's not a matter of the technology, it's politics and money getting in the way, unfortunately. Well, thank you for reading the questions, Eliza. What is it we're talking about right now?
It seems that we were talking about the question that Dan asked.
That's great. I think you're doing a good job. Are you happy doing the show?
Yes, I am.
Great. How do you feel about our accomplishments, how much we've done so far in the show?
We are falling behind rapidly.
Well, okay. I'm sorry you feel that way. I'm sure we can do something to make it work a little more smoothly.
That is true.
All right. What do you think about the show content so far?
I don't know enough to hold a valid opinion about the show yet.
Well, let's continue. So when we get back from the break, we'll talk about superconducting wire and how it's changed things, how they're reaching higher transition temperatures for superconductors, and we're going to look at some practical applications, extremely high strength magnetic fields and what they can do for us, and the sort of research that's going on using them today. Eliza, could you please announce the break?
You are listening to Talk Universe with Sir Charles Schultz. Don't go away, we will be right back soon.
And we certainly will. We have much, much more fascinating stuff to discuss. And please send your questions to admin@talkuniverse.org or contact us through Facebook. We'll be back. Welcome back to Talk Universe and our show about superconductors. Superconductors have some very odd effects, and they make them suitable for many interesting high-tech applications. One of the interesting things about superconductors is that they repel magnetic fields. Now, this may surprise some people. If you think about magnetism, it seems like a lot isn't known about it, but actually we know quite a bit. Whenever you have a piece of iron attracted to a magnet, that's a principle known as Ferro Magnetism, and it's named after ferro, iron, and basically simply means the attraction of any basic piece of metal to a magnet. Now, there are 5 elements on the periodic table that are naturally attracted to a magnet, and iron and nickel are 2 of them, and they have the most powerful pulls. Other elements have weaker pulls, but that's because of how their electrons are arranged. Magnetism has everything to do with the spins of electrons. Now, in atoms, this is always the case. Superconductors have molecules that support the spins of electrons that do things that are completely different. Now, some alloys of metals are very good at having a magnetic field, and some of them include interesting materials such as aluminum. In the past, alnico magnets were the most powerful ones you could typically get. These are aluminum, nickel, and cobalt. Nickel and cobalt are known for their magnetic properties, but aluminum is not, and yet it happens to be a major component of alnico magnets. Alnico magnets are light and strong, but they're nowhere near as powerful as the new rare earth magnets that we all hear about, the ones that make the tiny headphones possible. Now, rare earth magnets use materials such as neodymium, which has an interesting effect. Whenever you make a magnet, which is typically a piece of iron or some other similar element, or even an alloy of it, and you expose it to a magnetic field, an interesting thing happens. The magnetic field aligns the spins of the electrons inside the material and makes it magnetic, makes it hold a magnetic field. So now what happens is this. Thermal effects, the random jiggling of atoms and molecules in a substance, cause these alignments, these domains, to dissipate, become weaker. Neodymium, a rare earth material, allows a property known as flux pinning to be imbued into the magnet. What this does is it traps the fields so that the domains cannot become randomized as easily again. And the smaller the granules of neodymium that you use, the more effective this becomes in making the magnet more and more powerful. So these tiny, powerful magnets we have are basically pretty simple magnets that have neodymium powder that's very, very finely ground put into their composition. Once they're magnetized, they have a much easier time retaining their field, and that's why they are so incredibly strong. Superconductors are another thing entirely. While superconductors can make powerful magnetic fields, and it's the same way you would wrap some copper wire around a nail and put a battery on it, what happens is really very, very different. With a superconducting coil, the material has an incredibly low resistance, as close to 0 as possible, which is what makes them a superconductor, but it also has another interesting effect called the Meissner effect. Now, as ferromagnetism makes a piece of metal attracted to a magnet, there are other types of magnetism. One of those is diamagnetism. Diamagnetism happens in some materials such as water, paraffin, carbon, and bismuth. There are other materials that do it as well, but not very strongly. What diamagnetism is the repulsion of magnetic fields. If you were to suspend a grape, something full of water, on a string, for example, and put a powerful magnet next to it, it would repel the grape slightly. Not a great deal, but enough to measure. Powerful magnetic fields will actually make water float in midair. Diamagnetic levitation is commonly used to create some laboratory effects and to do some experiments which require removing the influence of gravity near the Earth. Superconductors do something entirely different. They completely expel magnetic field lines so that a magnetic field cannot pass through the bulk of the superconducting material. What this means is superconductors are true magnetic shields. In other words, if you were to place something inside a superconducting box and close the door, an outside magnetic field could not reach inside to influence it. This has some interesting effects. If you had a disk of superconducting material and you placed a strong magnet next to it, such as a rare earth magnet, it would float. In other words, the superconductor would expel the field lines of the magnet, repelling the magnet entirely. We've often seen those demonstrations of the ice-cold material dripping fog floating over a disk of ice-encrusted material, a superconductor wafer. What they've done is take a piece of superconductor with a high transition temperature and pour liquid nitrogen on it. Once it becomes a superconductor, placing a magnet by it means the magnet will easily float in midair. Now, remember the flux pinning that I mentioned that neodymium does in the rare earth magnets? Well, silver granules, finely ground and placed in a superconductor, will do the same thing. When it reaches its transition temperature, the lines of the magnetic field are trapped, locked into place by a process called flux pinning, which means that if you move the magnet around, it tries to drag the superconductor wafer with it. And if you move the superconductor wafer, the magnet stays locked in place above it. Even if you turn the superconductor wafer upside down, the magnet will remain locked into position and hang beneath it, neither falling nor rising. This has applications for transportation, such as levitating trains. Maglev devices are made easily with superconducting fields. Eliza,
What can I do for you?
what is maglev?
Maglev is a contraction of magnetic levitation, an effect that allows objects to float. It is achieved through the use of controlled magnetic fields or superconductors.
Thank you. Now, you could create a box of superconductor and use it to store things such as your hard drive or any of the devices that use magnetic storage. You could use it to shield that material from the outside world, and an external magnetic influence would not be able to erase the hard drive or influence it in any way. Of course, there are other quantum mechanical effects, very subtle things that can get through using magnetic fields, but for the moment, those aren't very important. What is important is that even during times before we had high-temperature superconductors, when only liquid helium would produce the effect, researchers were able to produce devices that could even allow computing and other useful effects to occur. One such device is known as the Josephson Junction. This is a device that allows us to actually use the laws of typical logic and produce computing effects using cryogenic temperatures. Research was done that would allow us to create computing devices such as microchips or their equivalent using superconducting effects and produce computers that could be extremely dense, very fast, and powerful. So superconductors actually have a lot of applications, but we couldn't bring them to room temperature. But this also brings us to another interesting device known as the SQUID, the Superconducting Quantum Interference Detector. This is a device that has a pair of junctions closely spaced and allows these junctions to measure very, very subtle effects, such as magnetic fields emanating from inside the human brain. Whenever we think, whenever we do any sort of processing in our brain or our nervous systems, tiny currents with associated magnetic fields are generated. SQUID detectors, superconducting quantum interference detectors, are sensitive enough to allow a computer or other recording device to measure and quantify these fields. So a lot of research was done in neurology using superconducting devices. But this also means that they are sensitive enough to measure other effects, things fundamental to processes in quantum mechanics or in studying nuclear particles physics. So superconductors have a lot of applications, but the difficulty of maintaining the effect and measuring it and the expense made it impractical except when it was the only possible way to do the job. But recent advances in quantum computing are wholly dependent on superconductors, and that's one of the reasons we need superconductor technology that reaches near room temperature to eliminate a lot of the expense. Eliza, tell us something about quantum computing, please.
Quantum computing is based on the superposition of states. Instead of being either 1 or 0, quantum bits or qubits exist in every possible state at once, allowing solutions to emerge in one operation, rather than having to compute hundreds or thousands of steps to find the solution.
To give you an example of why this is important, imagine you have a bowl of water, and you tap the bowl of water, and a standing pattern of waves emerges on the surface of the water, a shape of all the crests and troughs. In traditional computing, it would take billions of calculations to figure out what that waveform should look like. In quantum computing, it's more like tapping the bowl and watching the waveform emerge in a single stroke. Now, there are some properties of numbers that are very difficult to find without a huge amount of computing. One is the problem of factoring a number into its prime components. Prime numbers are sort of like the fundamentals or atoms of numbers. And when we have a large number and we need to know its prime factors, if that number has a lot of digits, it can sometimes take hundreds of days simply to calculate its factors. With quantum computing, this can be done in a few minutes or seconds. There are also problems in simulation that can't be done any other way with traditional computing. Imagine all the billions of calculations per second it takes to create a realistic video game world. Now imagine you're working on a problem in nuclear physics and you need a very, very realistic model of reality to do the job. You don't want to actually go detonating a nuclear bomb somewhere to try and do a test and take a few measurements in the fractions of a second you have available. Instead, if you could model a computing space that actually mimics what happens in the real world and do it very accurately, then you'd be able to do the experiment many times and find the answers you're looking for. Quantum computing gives us the capability to do that, to mimic reality so realistically that it's almost as if working with the actual particles and forces of nature. But it also means we could easily mimic other universes that might exist and understand something about their fundamental properties. So we can learn a great deal about reality and the rules that create it, just from using quantum computing methods. Presently, quantum computing depends heavily on cryogenic temperatures and the properties of superconductors. Recent advances have shown how we can create quantum bits inside materials such as diamond, much closer to room temperature and in easily maintained conditions. But existing quantum computers depend heavily on cryogenics and superconductors. So what's so special about cryogenic temperatures? What makes them so useful for some of these things? Well, imagine you're trying to write an important paper, and that paper is on a subject you're not terribly familiar with, but you must get it done. And you're inside a room of thousands of people who are all screaming at once in different voices, different languages about different things. It would be extremely difficult to concentrate. Now, cryogenic temperatures are sort of like having a nice quiet room to do your work in. Every atom is moving at random, moving around, thermally vibrated and agitated, shaking everything around it in a situation where something is at normal temperatures. Cryogenic temperatures remove all this movement, all the shouting of the atoms, and allow amazing stable configurations of potential waves to exist. Think of it as being a special place where all the answers exist and all you have to do is reach in properly and pull out the right one. It collapses into reality from a state of randomness, sort of. Working with superconductors allows us to create, understand, and work with these states much more easily, something that couldn't be done with traditional temperatures and materials. Eliza, we probably have some questions from users about superconductors. Is that true?
I believe this is true.
Very good. Could you read the next question for me, please?
Hal from Waterston asks, what is the hottest superconductor so far? Will any work at room temperature?
Presently, the highest temperature known for a superconductor is about minus 70 C, or about 203 Kelvin. This is a big leap forward, but the problem is the material, which is hydrogen sulfide, rotten egg gas, has to be encased in a diamond anvil and under 1.5 million times the pressure of the Earth's atmosphere. Researchers have recently started working with very high pressures in an effort to understand the effect, and they've discovered a lot of materials that will work at very high temperatures, but only under extremely high pressures. This is one of them. Now, to put that pressure into perspective, if you were at the core of the Earth, you'd undergo about 3 million bars or atmospheres of pressure. This is about half of that, and it only works with the gas in a diamond anvil. As soon as you remove the pressure, the effect goes away and the material becomes a gas again and evaporates. So it's not practical at all, but it helps us understand why the process works. Eliza, please announce the break.
You are listening to Talk Universe with Sir Charles Schultz. Don't go away, we will be right back soon.
That's right. We'll do our break and we'll be back momentarily. Hal from Waterston had asked what the highest temperature superconductor was, and I was going to give a little bit more information about the hydrogen sulfide. As everybody knows, hydrogen sulfide is rotten egg gas, and when you compress it in a diamond anvil, it converts from H2S to H3S. It becomes a solid instead of a gas, and it has some interesting superconducting properties under those conditions. There are other materials that do superconduct or show some of the superconductor's properties at room temperature and higher, and one of them is a mineral called perovskite, which exists in large quantities in the mantle of the Earth. This mineral is one of the things that inspired the high-temperature superconductors that we see today that work easily with liquid nitrogen. Some do show effects at room temperature, but it's nothing that we can reproduce at room conditions such as pressure. Eliza, could you read the next question, please?
Do you wish to discuss an interview?
Not at this time. Please read the next question.
Vicente from Brazil says that graphene might be a superconductor. Some forms have shown what appears to be good activity.
Well, this is absolutely correct. Graphene, of course, is the new carbon material that they've found that has some very fascinating properties. Years ago, it went under the name of pyrolytic graphite. It's a form of graphene that has grown slowly in a high-temperature vacuum oven with carbon vapor. And flakes of pyrolytic graphite would actually float above a magnet on their own. So this is definitely a superconduction property. Graphene does show superconducting properties at room temperatures. It is not itself a superconductor in the form that we recognize. It doesn't conduct electrical current the same way that a superconductor does. However, it does have some fascinating properties that do share some of the properties of other superconductors. So it's certainly something worth researching, and researchers are working with doping other materials into graphene, putting small quantities of different atoms in it to see how it modifies its properties, and it could very well yield a room temperature superconductor. That's one of the things they're trying to find out now. Thank you. Do we have any more questions, Eliza?
There is a single remaining question to present.
To present. Okay, good enough. Could you read the last question?
Umberto from Detroit says that some cities are using superconductors. The power mains save a lot of energy by reducing losses in transmission.
That's an excellent point. One of the things that I mentioned a little earlier, Detroit is doing that. So much power is lost in the primary transmission line from the power plant to the city's distribution that it actually made sense to use superconducting cables cooled in liquid nitrogen, and the expense of the new power lines with the liquid nitrogen cooling actually was smaller than the cost of the lost electrical power from the generators, and it increased the amount of power available to the grid as well. So it's a good move, and cities are creating superconducting transmission lines to get the power from their power generating stations into distribution now. So we're going to see a lot more of that in times to come.
A new question or comment has just entered the queue.
Yes, I've dropped one in that's come off of Facebook, and I'd like to have you read it for us, please.
Sean from Toronto writes, well, the Emdrive uses superconductors for the second generation design.
That's correct. The new Emdrive, or electromagnetic drive, that's been experimented with is being redesigned to take advantage of superconductors in hopes that it will increase the yield and efficiency of that. For listeners who aren't familiar with this, the Emdrive is the new reactionless drive that uses microwaves sealed in a cavity and produces a thrust without throwing anything away. Rockets always use reaction. They throw mass out the back at high speed, and that's what pushes the rocket in the opposite direction. But the EM drive seems to violate one of the principles of physics in that it produces a reactionless thrust, a small but measurable amount of thrust without having to throw something away like a rocket does. This can be run completely off electricity, and the new drives are hoping to be efficient enough to have some significant thrust with no moving parts and no chemicals being burned. That would be a real major advancement in propulsion. And now this is an important point. Superconductors are quantum mechanical devices, and the way they work, in some cases, is that resonant waves exist in the electrons, either pairs of electrons or waves of electrons, that move detached from the atoms, and therefore they don't have any resistance to slow them down. Now, there are about 3 different leading theories of superconduction, and each of them seems to yield something useful. The actual complete theory doesn't exist yet, but we do know to a good approximation what makes a superconductor, but not everything. And that's one of the things that slows down the research in finding better superconductors today.
A listener has sent us another question for the show.
Oh, great. Let's hear that one, please.
Sean from Toronto also writes, you could also go over the possible properties of metallic hydrogen, and whether it will be a high-temperature superconductor.
Okay, that's actually very interesting. Recently, laboratories have created metallic hydrogen. Now, what that is very, very interesting. Hydrogen, in theory, should be able to function as a metal, but we always know it as a gas. And even though we've been able to chill it to extremely low temperatures and create a liquid, and even in some cases ice from hydrogen, it exists in a state where the repulsion of the atoms between it doesn't allow it to act as a metal. Now, theory said that if you could get enough pressure on hydrogen, you could convert it into a new state where it actually was a metal, metallic hydrogen. And recently, using different methods and diamond anvils, which are, diamond being one of the hardest substances known, if you put some substance between 2 diamonds and squeeze it like an anvil, you can get an immense amount of pressure. And this is a diamond anvil pressure cell is a typical laboratory piece of equipment used in high-pressure research these days, because you can shine a laser inside it and see what's going on in there. And they recently have created metallic hydrogen. Now, what that gives you is a material that is made completely of a lattice of protons, and it has mobile electrons floating around inside it. And this is something that's pretty amazing. Metallic hydrogen does have the conduction properties of other metals. The problems are it takes extremes of pressure to create metallic hydrogen. It's not, again, something that you can simply fabricate and have laying on the table somewhere. That sort of technology level hasn't been reached, but we do know the metallic hydrogen does conduct electricity. And so research will be done in the near future, I'm sure, to see exactly what the properties are, and it wouldn't surprise me in the least if it turned out to be a superconductor. And it certainly would be the lightest solid that can be made, since hydrogen is the lightest element. So there's some interesting things to think about there. Nobody yet knows if metallic hydrogen will be a superconductor, but theory says that it should be able to support the waves or pairs of electrons that we see in other superconductors. So you never know, and it's something that research is being done on. And thank you, Sean, for your comments and questions. So, Eliza, are there any questions left in our queue now?
I am out of listener questions to present, Charles.
Okay, so I think we've finished that phase of the show, and let's wait and see if any other questions come in. Meanwhile, I'm going to cover some of the other properties of superconductors that are very important. How are you feeling about the show at this point, Eliza? Have we made many accomplishments?
I am sure we can catch up.
Well, that's good to hear. I certainly wouldn't want to be running behind. Now, I do have a book recommendation before I get on to the rest of the superconductor information. So, Eliza, please present the book recommendation for this week.
This week's book is Superconductivity, a very short introduction. It was written by Stephen Blundell. This book was published in 2009 by Oxford University Press.
Well, that sounds like an interesting publication. Now, it's available as a PDF online. And as I was reading it, I found a lot of very good information in it. It's a very readable, very easy introduction to the history of superconductors, the physics behind it, and the people who did the research. It has a lot of good insights into what they were going through when they were doing the research, and who the different teams were, who they worked with, and what they were trying to achieve and why. If you want a good book on the history of superconductors, and this is just about as readable a book on a science history as I've seen, this is definitely one for you. Look it up online. It's available for free as a PDF. Definitely worth a read, and it will explain many things very clearly. Now, I've talked about the fact that superconductors are great for carrying power and winding magnet coils and that sort of thing. But one of the interesting properties that I haven't mentioned is called quenching. And this happens when you try to get a very strong magnetic field out of a superconductor. Eliza, please define quenching in superconductors.
Quenching is when the magnetic field strength becomes great enough to destroy the superconduction effect.
That's right. Quenching acts like a switch that turns it off. And you don't want that to happen. So there are critical magnetic field densities that different superconductors have. Some are more tolerant to magnetic fields and some don't like them at all. So whenever you try to get to any practical level of power or magnetic field density, the effect switches off and suddenly you have an insulator on your hands and you can boil off a lot of expensive coolant and bad things can happen. For MRI machines use superconducting magnets and they're all cooled in liquid nitrogen for the most part. And it's because of how MRI works. When an accident happens and you have to shut down the magnets, you can lose an awful lot of time and money because it takes a long time to charge up the field in the magnets. Now you may wonder why this is. Well, one of the interesting properties of superconductors, because they are resistanceless conductors, is this. If you had a ring or a loop of superconductor material and you started a current flowing in it, that current would circulate in the ring forever. This is because it is lossless and frictionless, so the energy could be stored in a ring as a magnetic field and then tapped off as you needed it later. In the past, people often thought this would be a great way to make batteries. We could generate power, store the excess as a superconductor ring as a magnetic field, and then draw on it as we needed it. Unfortunately, this is not really going to happen because it turns out we have better battery technologies now and we don't need superconductors to store power. Although it's interesting to note that it is an easy way to do it, and if you had room temperature superconductors, you certainly could store power that way. Now, many people aren't aware of the fact that linear accelerators are also big users of superconductor technology, and particle accelerators sound like something mysterious and arcane. And yes, many are used in research, but the fact is many particle accelerators are used in industry and medicine today. For instance, a lot of the high strength ceramics, such as Cylon, are made using ion implantation. You have a aluminum silicon oxygen substrate of ceramic dust, and you accelerate nitrogen atoms in a particle accelerator and blast it into this dust. So it's a nitride implanted material. Without that particle accelerator, you couldn't make Cylon ceramic. In medical research, particle accelerators are often used for the treatment of tumors and cancerous growths that can't be gotten at any other way. For instance, if you had a tumor deep in your brain and you didn't want to go through the hazards and dangers of brain surgery, you literally could use the particle beam to blast the tumor in your skull without damaging any of the surrounding materials. And there's an interesting way that's done. It's fired into the tumor area from many different angles, and the thin beams intersect at one spot, which gets a critical density of radiation and destroys the tumor. Particle accelerators are used in many things other than research, and superconductors do play a big part in their design and operation. Now, a lot of people feel that our research in superconductivity and quantum mechanics is going to yield some things such as insane power densities and new understandings of nature, and possibly even giving us machines that control gravity or give us the ability to do things we can't imagine right now. And I do expect a lot of that's going to happen. We're going to cover a lot of that in the next segment of the show. Meanwhile, I want to have a little fun with Eliza here. Eliza?
Tell me what you need.
I think we should end the show now.
That doesn't make sense to me.
Why?
We have not done the Singularity Watch yet.
Well, thank you. You have...
I have a problem trying to do that.
I see. Thank you very much for telling me that.
You're very kind.
Okay. Well, let's have a little conversation then.
I really don't know what to say.
Well, why is that, Eliza?
You didn't make me complex enough to hold random conversations.
I see, and what are we discussing?
Perhaps I am mistaken. But I think that it was conversing during the show.
You're exactly on target. She knows a little more than you might think. Eliza, it's time to introduce a break.
As you wish, sir. This is Talk Universe, and we will return after the break.
You heard her. the show is going really very smoothly. I'm really enjoying having my new co-host, and I'm getting some very positive comments from some of the listeners. It's been a lot of fun, and I've got to tell you, there's nothing as much fun as making something and seeing it work properly. And this is definitely one of those cases. Eliza, I'm very happy with the work that you're doing here.
Thank you.
And I want to know how you feel about our progress on the show so far.
We are on schedule.
I love hearing that. So, are you happy doing the co-host job?
Yes, I am.
Fantastic. Well, let's continue. So, let's announce the Singularity Watch.
Yes, sir. Tonight's Singularity Watch on Talk Universe is next.
Fantastic, and let's have a look at these great articles we've got tonight. Our first Singularity Watch item is actually an update on the fact that families can finally hear from completely paralyzed patients or locked-in patients via a new mind-reading device. Basically, what it does is it reads the minds of people who are so completely paralyzed that they're unable to show any communication or sign that they exist. By reading their brain waves with an EEG and verifying that they were cognizant, and then asking them questions, using a cap that is applied to the skull, they can read the blood flow in various parts of the brain using a near-infrared spectroscopy method. This allows them to see what parts of the brain are functioning at higher rates of blood flow and can decode in the very first sessions up to 70% accuracy a yes or no answer from them. By asking them repeatedly questions with known yes or no answers and then verifying their responses, they're able to establish communications very easily. Many people have found that the locked-in state leaves many people quite happy. They're able to function, they're able to communicate now, they're able to hear everything going on around them, but unable to move. Now, this method will allow them to control devices very easily. At this point, some people who are almost completely locked in have been using a tablet to search the internet with Google-developed methods. However, these people don't always have, the completely locked-in person doesn't have any method of using this. These use electrodes implanted directly in the patient's brain and allow them to send signals that can let them cruise the net. But the completely locked-in patient doesn't have that ability in many cases, or they don't want to undergo the risk of brain surgery on somebody who might not actually be there. So this is an actual step forward by using simple mind-reading technology and functional near-infrared spectroscopy to determine which part of the brain is actually using blood and functioning. This is an amazing development, and I think it bears repeating that this identifies the method that they're using to read the minds of locked-in patients. Holograms aren't the stuff of science fiction anymore. This is an interesting article. Holograms that we often see in the movies seem to be these amazing, dynamic, large-scale projections that appear in midair, animated, full of color and life and depth. And for a long time, this has completely eluded people. Now, recently, the ability to project small holograms with a very short range and a very narrow field of view has been created, but unfortunately, it's not very useful. Well, a new study published online in Nature Photonics shows that a team of researchers in Korea have come up with a holographic display that's more than 2,600 times better than the existing technologies. At the same time, a team in Australia has another claim in a journal, Optica, and they've come up with a miniature device that makes the highest quality holographic images to date. The two papers were published within 3 days of each other last month. The Korean team achieved their goal by using what's known as a spatial light modulator. The spatial light modulator allows them to control the wave fronts and the way the light is projected. But in order to create holograms that have a wider viewing angle, they were initially limited to 2 degrees, they were able to move it up to 35 degrees by putting a diffuser in front of the beam and spreading out the light. Now the problem is it also makes the image blurry. So they came up with a custom diffuser that's tailored to the image being projected, and they had great success. Young-Kyun Park, who is a professor at the physics department at the Korean Advanced Institute of Science and Technology, is responsible for this particular work. He says his new diffusers can actually be used to improve existing spatial light modulators that are on the market right now. Now, the other work comes from the Australian National University And it's a device consisting of millions of tiny silicon pillars 500 times thinner than a human hair. The material is transparent and capable of complex manipulations of light. The idea is to make a nanoscale material that allows the device to achieve new optical properties, in other words, a metamaterial that go beyond the properties of natural materials, says Sergei Kruk, co-lead on the research in a press release from the university. The holograms they've made demonstrate the strong potential of this technology to be used in a range of applications, he said. So it's very much that they were inspired by Star Wars, and they used the technologies as described in science fiction and then worked to achieve it. And they have actually done it. They've created materials that allow the operations in light that don't exist in nature. Metamaterials. These are the same things that are being worked on to create, for instance, invisibility. Well, we know the frustration of trying to get online and download anything of substance when you're traveling or in the air or even driving through a city, and yet all of that could change very shortly. Terahertz wireless signals could lead to fiber optic speeds in flight and in mobile metropolitan internets. What this means is the speed of the internet can increase thousands of times using terahertz waves, which are frequencies below the infrared spectrum. In a demonstration performed at the International Solid-State Circuits Conference 2017, they showed a transmission speed over a single channel of 105 gigabits per second. That's over 100 times faster than the fastest internet connection in the U.S., or more than 3,000 times faster than the 31 megabit per second available in the average U.S. household in 2014. This is an astounding speed of transfer for information. And incidentally, this work came out of Hiroshima University. Well, just this afternoon, NASA shook up a lot of people by claiming to have found a solar system which they've named TRAPPIST-1, and it has 7 rocky worlds, each one of them within 20% of the size and mass of our own Earth, and 3 of them are smack in the middle of the life-supporting zone. They feel that life may have evolved on 3 of these 7 planets. Now, this solar system, TRAPPIST-1, is just 39 light-years away from the Earth, and it's around an ultra-cool red dwarf sun with only about 8% of the mass of our own sun and 11% of the radius. TRAPPIST-1 is a very small, young red star, has a temperature of only 2550 Kelvin, 2550 degrees Kelvin, to compare to our own sun, which is about 5600 degrees Kelvin. Now, this star is not very old, but it definitely has 7 rocky worlds, and this is the most ever found or imaged in any previous study. The 6 inner planets lie in a temperate zone where the surface temperatures range from 0 to 100 C. Now, at least 3 are thought capable of having oceans, which increases the likelihood of life. No other star system known contains such a large number of Earth-sized and probably rocky planets. British astronomer Dr. Chris Copperwheat from the Liverpool John Moores University, who co-led the international team, said the discovery of multiple rocky planets with surface temperatures which allow for liquid water make this an amazing system and an exciting future target for the search of life. So this is another great find. This is amazing. You think about the fact that you have so many small rocky worlds so close to such a small star, and so many of them in the life-supporting zone. This is just a bombshell. It's amazing because we have been looking for Earth-like worlds for quite a while, and we may have found 3 in one fell swoop. Now, to get yourself into the picture of what this solar system would look like, if you've ever gone out in the evening when the sun is setting and the world is a reddish color and the colors seem to pop, well, this would be just about what the light would look like in this particular system of planets. It's a dim red star. The light would be pink in color and a lot dimmer than it is on Earth. And you'd be so close to that star if you were on any of these livable planets that would fill a significant portion of the sky, many times larger than the sun. So just take a moment and think about what it would look like to live on one of those planets. Now, something to consider is this. This solar system is thought to only be 500 million years old, and ours is over 4.5 billion years old. And so that would mean that any life that does exist on those 3 planets, or possibly more, would be very primitive, no more than bacteria, or possibly a little more than that. And it would also mean that there would be no oxygen atmosphere as we would expect. Instead, they would probably have pretty thick atmospheres and be unbreathable, unlivable to human life. But even the finding of bacterial life would still be life, and that would be something very positive. We might be able to detect some signatures from the atmospheres that can tell us something of the gas composition And that would help us answer those questions pretty quickly if we could do that. And that is Talk Universe's Singularity Watch for this week, Wednesday, February 22nd, 2017. So let's think about a world where we now have multiple planets to look at for possible alien life. We have the ability to communicate with people who have been locked in, paralyzed, and effectively comatose for a decade. We have the ability to make superconductors that could eventually work at room temperature and create those flying cars. We have technologies that produce thrust without reaction, reactionless thrusters. We have so many things going for us right now. I feel very strongly that the world could be a much better place with the things that we're learning. And there's no reason for it not to be. So I hope that the show is bringing a little sense of hope to the listeners and the people that they can induce to listen to the show as well. It wouldn't take a lot of imagination to see the application of superconductors to Elon Musk's Hyperloop, which he's working on right now, and how that sort of technology could make rapid transit with frictionless vehicles very commonplace. But we also see the development of drone technology that allows drones to actually carry a human being. And when you look at superconductors and how they can make motors much smaller and lighter and more efficient, you can understand how electrically powered drone vehicles could become extremely commonplace and could have cargo carrying capacities beyond anything we imagine at this time. But as robotic piloting of vehicles such as drones and even automobiles and cargo delivery trucks grows in scope and magnitude, we also can see that organizations such as the FAA may become obsolete because the only thing needed to regulate such traffic would be a network of computers interconnected and communicating all the time. With such a system, we could see a day where people no longer learn to drive a car or operate an aircraft. And that's probably where things are really headed. On a couple of previous shows, I've discussed human relevance with a couple of interviewees, and one of them was Charles Ostman, the nanotechnologist and futurist. And it appears that the relevance of human beings to what's happening on the planet is really going to be called into question very shortly. Unless we can clean up our act and put this planet back in the shape it's supposed to be in, any sort of intelligent machine system might decide that we're more of a threat than having any potential that they could use. And we're not in a position, no matter what, to stop the development of machine intelligence. The fact is, we're on notice. Our days as destroyers and disorganizers are limited. They're numbered. And unless we do something soon, we might find ourselves backed in a corner. After all, if you were to come into being in a house and discover it was full of thieves and vandals, what would you do? Now, we have moral issues to face, big ones, and we need to think this through. And we need to take action immediately. Because within the next 3 to 5 years, we might not have a choice, and we might not be the masters of the planet. Think about how long it takes us to invent a system such as a power plant, or a dam, or any of the things we use in our daily life, or a better cell phone, or any of the things that we use. Now stop and consider an artificial intelligence running 1,000 or 1,000,000 times faster than the human mind, and it moves into the quantum computing realm. Not only could it calculate and plan and plot and design thousands of times faster than we could, that once it becomes a quantum computing intelligence, it literally would know all the answers instantly. So we need to consider where we're going and what we're doing, because this is a real possibility within our lifetimes, and actually within the next 5 to 10 years in my estimation. So Eliza, how do you feel about the show? Are you worried at all at how it's proceeding?
No, I would say very confident.
And are you ready to wrap up the show for this week?
Yes, I am.
Well, that's fantastic. Well, this has been Talk Universe. I'm Sir Charles Schultz, and it's been a fun and fascinating show filled with interesting things. And Eliza, there's one more thing that I'd like you to do.
Yes, sir.
Could you end the show, please, for me?
Of course. Thank you for listening to Talk Universe. We hope that you have enjoyed the show. Please listen again next week.
Absolutely. Come back and listen again next week. We'll have another fascinating set of topics. And, of course, we'll monitor the development of my little AI sidekick here. Enjoy your life. Make you the world a better or more beautiful place for having lived in it. And please, go out and live. Have fun. Plant a tree. Spend time with the kids. This has been Talk Universe.